Hi, everyone. Welcome to San Diego Machine Learning. Ryan and I are organizers for this meetup, and we're very excited today to talk about the team that we participated in that came in first place in the recently completed Kaggle competition, the Vesuvius Ink Detection Challenge. So we're going to start with just a brief introduction about what the competition was about, and then we'll go into details about our solution and invite others to also share about how they tried to tackle this problem. So just to level set, we've got a couple different audiences here. So we have some people from the San Diego community, people who did not participate in the competition, as well as people who did. So just to level set, we're gonna start with this so that everybody has like some basic shared information. Okay, so if you guys can all see my screen. So the competition just finished this week, and this was a competition. We're very excited about this Vesuvius challenge, of which the Kaggle competition was just one component, okay? And the idea is that in 79 AD, most people have heard of Mount Vesuvius.
Are you meaning to be sharing, Ted? Sorry.
Yeah, we can't see your screen.
You cannot see my screen. What is going on? Oh, sorry. Let me back up. That's probably
there
a lot
we go.
better, huh?
Yeah,
now we can see it.
Perfect.
Yeah. Nice.
All right. I've only been doing Zooms for like 4 years. You'd think I'd get the hang of it by now. All right. So to level set for everybody, we have this wonderful challenge. And the Vesuvius challenge, the Kaggle competition was just one component of this, okay? And so I think most people have heard of Mount Vesuvius, 79 AD. The volcano erupts, and lava, mud, ash, all of these things descend on Pompeii, Herculaneum. And in 1750, somebody's digging a well and they discover, okay, there's ruins. That's not like surprising. But what's really cool is that in here, there's a library and there's hundreds of scrolls. And while scrolls like just left in general, like on a shelf in Italy, right? The air, the moisture would have like completely deteriorated them. To a certain extent, they've been destroyed by the volcano, but to another extent, they've been frozen and preserved. Okay, so these carbonized scrolls, a number of them have now been recovered, and there's the possibility that there's even more as you know, archaeologists continue to find more sites in the area. So 2015, the idea is that so over the years, people tried to like see if they could open them up, and of course, you know, they've just been seared into a solid cylinder, and so for the most part, you just can't do it. It's gonna crumble, turn to dust. You're gonna destroy them in the process. So then the idea is with the technology that we have, we can now sort of take something on the left that looks like, you know, something from the cylinder, and we can virtually, you know, unwrap it so that what we have is the equivalent of the physically unrolled scroll, a nice vertical rectangular representation without actually physically taking apart the papyrus. And so we can use a particle accelerator, very high energy particles in order to do high resolution scans. There are a number of scans that were done, 8 micron, and for this competition, we were actually fortunate enough to have 4 micron scans of the papyrus cylinder. Well, these were fragments that were actually separate from. So the idea is basically you scan it, use some kind of advanced machine learning model, and you can detect where there was ink, where there was not ink, and then we would be able to read these scrolls. So here comes the Kaggle competition. We have these fragments, and the cool thing about fragments, as opposed to the scrolls that are still just like in one big cylindrical chunk, is that people have found you can use infrared light to look at the pieces once they're opened up, and some of the ink is detectable. So what you would hope is that you know, this on the left, that you sort of see something in the sort of 3D, you know, X-ray scan that we can confirm with the infrared. So the ink, some of it does show up on infrared, but the problem is you have to open it up in order to use infrared. Infrared won't penetrate the cylinders. Unfortunately, the problem is most of the scans look like on the left, and you can't see where the letters are. You can't see where the ink is. So in terms of machine learning, for those of us who are, you know, familiar in studying machine learning, this is a very standard supervised learning problem. Okay, we have data and we have handcrafted labels that tell us what the ground truth is. So here there is ink, here there was not ink. Now in this case, we do think that there is likely some error in the labels. So we have to take that into account. There's some places where maybe there is ink and the infrared scan, we couldn't see it, but there really is ink. And so even if we correctly predict that there's ink, the labels will tell us we're wrong, that it was a false positive, and vice versa. So it's a bit of a noisy problem. So what we've got now down is the cylinder. The plan is to, you can see sort of layers of papyrus and then air and then papyrus and air. So to virtually unroll that spiraled up cylinder into a big giant rectangle and then be able to apply these techniques. So the Kaggle competition involved just this part of it, okay, which is if we can unroll it and just give you a nice sort of flat scan, where is the ink? All right, and so here's a sort of a better picture to see sort of like you've got the fragment, we're gonna align it with the 3D scans, and someone is going to painstakingly handcraft labels to tell us where the ink is. Again, so these are our Ys, these are our ground truth labels. Just another little bit of level setting. So in computer vision, there's lots of different tasks. The 4 biggies are image classification. So is this a cat, a dog, a rose, a tree, right? We have object detection where we find the particular objects. So like you would imagine self-driving cars, it's very important. This is another car, this is a pedestrian, this is a dog. We have semantic segmentation where you're sort of finding each pixel that belongs to a particular class. And then instance segmentation is a slightly more complex version of segmentation. So this competition was about semantic segmentation. We're just saying ink or no ink, okay? And so ultimately, this ends up being a binary classification problem for each pixel. And a common architecture that we use for semantic segmentation is the unit architecture. And so you'll see that a lot of people use this and variations of it. The left-hand side of the U looks a lot like a regular convolutional neural network. You'll have convolutional layers, max pooling, and until you get to a representation that has more channel depth, but is much smaller in terms of the X and Y, the height and the width dimensions. What makes a UNet different from a CNN is that it then has an upscaling side on the right half where it goes back to the full resolution, and, but in a separate, different from like maybe just simple super resolution, because we know we're starting with the full res image, it has these skip connections that are portrayed by the gray arrows going across here. All right, and then finally the competition, it started March 15. It ended this past week on June 14th. And I wanted to mention that our metric for this was a modified dice coefficient. And so it was modified to emphasize true positives a little bit more. And I think later on in the discussion, if other people don't mention it, I have a few comments in terms of this actually is a somewhat of a difficult metric in order to optimize in terms of the competition. All right, so then these are the links where some of this information that I just shared came from. And I will put a link into the chat in just a moment for these slides that I just shared. So then you don't have to copy these down. You can just click on them from the presentation that I shared. And then finally, I'll just say at a high level for this meeting, I think there's probably going to be two types of things that people are going to hear about. So one is, how do you solve a semantic segmentation problem like this? And this problem's a little bit different. So there's a lot, if you think about like self-driving cars, there are a lot of models out there that are expecting 3 color channel inputs and a lot of different classes. Okay, bicycle, dog, pedestrian, that sort of a thing. And then there's like medical imaging where you're expecting grayscale images and depending on the application, maybe you only have one class of interest, like, you know, you're looking for nodules for lung cancer or something like that. There's many more 2D than 3D segmentation models. So I think that's one of the things that'll come up. But again, there's going to be the machine learning discussion. And then I think there's going to be a little bit of discussion in terms of, hey, if I'm interested in doing a Kaggle competition, there's kind of doing well with the machine learning. And then what are some of the things that we did in order to sort of squeeze that last bit of performance out? And I think other people will also be able to share in terms of not necessarily your basic machine learning techniques, but like how to do better in Kaggle competitions. So that's my general overview. I'll stop sharing my screen and share the link to the slides that I just shared. But any high-level questions just about the competition, anything I missed before we kind of get into the more technical details? All right. So then I think what I'd like to do is have the other team members introduce themselves. Just say hi, say a little bit about yourself, and then we'll go into Ryan's presentation. So we don't have a particular order. Alex, Ina, why don't you guys say hi first, and then we'll
Yeah, sure. So I'm Alex. I moved to San Diego like a couple months ago. Both of us got into the San Diego machine learning community, and that's how we met Ted and Ryan. I have a master's from Hopkins in biomedical engineering with a data science concentration. And my undergrad, my master's was all on network related stuff, so graphs with nodes and edges, and so this has been really fun. I've learned a lot from this competition.
Oh, we can't hear. Ina, I don't know if you need to be more central in front of your computer.
Yeah, maybe. Sorry. So hi, I'm about 3 years ago, and I work as a data scientist in a company that does AI for veterinary X-rays. So this is kind of like my field. I love X-rays. I've done a lot of stuff with X-rays. So yeah, it's been really fun, and it's been fantastic to work with Ryan and Ted. It's a great mentors. I really appreciate that.
Yeah, second that.
Awesome, thanks. And I'm sorry, I know we still had a little trouble with your audio. I apologize for that. I'm Ted Key. I work in healthcare, and at my company, I lead sort of our healthcare analytics and our data science teams, and been active in the San Diego machine learning community for a number of years. And so it's a lot of fun to see a few new faces. I'm glad that the Vesuvius competition brought a few new people here together. And then Ryan, why don't you say hi, and then you can just kind of go into your presentation.
Yeah, sounds good. All right, I'm Ryan Chesler. I've been around on Kaggle for a long time now. I started my machine learning journey on Kaggle. I kind of didn't go the academic route. I just learned from doing a lot of competitions and stuff. And then now I work at H2O, who obviously really values having grandmasters and Kaggle participation. So I've been kind of dormant all through COVID. I just haven't had the motivation. I've been doing more regular work, and then Alex and Ina popped up, and they were all motivated to do competitions again. And so that kind of pulled me out of retirement. And so I had a lot of fun with this one. We hung out at coffee shops, and we worked on this stuff. So I'm glad that I got going again, and I'm glad that we did so well. We had some periods where it didn't seem like it was going to work out, and then suddenly we kind of had our breakthrough, and then got back up on the leaderboard, and then I think that motivated everyone to keep going. And I will start sharing my screen, and we can get into the content a little bit. Let me make sure I have the chat still. So yeah, we did well in the competition. We got first. We spent a lot of time on this. And I'll just kind of go through. Ted already gave us the overview of the problem, but I just kind of wanted to reiterate this. So the data that we had 3 fragments of this scroll, and basically we have the 3D, each a bunch of TIFF files. Each of them is a layer of this scan of different depths. And so you can see what this sort of looks like in this GIF on the left. You can see the texture changes as it goes through the layers. And so it's you can't see any letters out of this, but in theory, there's some writing in there that you have to kind of figure out based on this texture that's going across the layers. So you pass this into a model, and this is some 3D input at some volume. And then you're trying to map it down to this final output. So you're saying in this 3D volume, for this XY pixel, is there any ink in that whole depth? So this is ultimately what we're trying to predict in the end. We want that full segmentation map in 2D. So just a couple details about the data and its properties. So we have the 3D volume input, we have the 2D segmentation output. And so this kind of complicates things because there's a whole bunch of 3D techniques and there's a whole bunch of 2D techniques, but there's not really a ton that go from 3D to 2D. And so we had to kind of innovate a little bit on that and understand how do we bridge the gap there. Because if we had 3D labels, then we might be able to just do this in a single shot with the 3D model and all of the stuff that's been used for medical research. But instead, we kind of had to figure out like how do we map this 3D down to 2D in a way that gets us the best accuracy. So each of these fragments had different height and width, and we actually had fragment 2 that was way, way, way bigger than 1 and 3. And so people were trying to figure out how do we handle this, because a lot of people kind of their first thought is, okay, we have 3 bits of data, take each of those as a fold and then train against 2 and validate against the third. And then that turns out to be a big problem because you end up with, if you train against 1 and 3 and validate against 2, you hardly have any training data. So your model doesn't turn out very good. And you have huge variance between all of your folds. So we had to be a little bit more thoughtful there. And I saw in the discussion, people are doing all different kinds of configurations. So one of the difficulties with this is we had these 65 layers, and some of them had ink, some of them didn't have ink, and we didn't know which was which. So we kind of had to pick and choose and analyze and understand where exactly everything was coming from. So the original scans were 16-bit. And so if you have a 6 by 8K by 65 depth, 16-bit thing, like it doesn't fit on many systems. Like if you have a whole bunch of memory, great, you can fit it in, but if not, you're kind of screwed. So I think a lot of people might have tried to train against the data with the Kaggle systems, and it only 13 gigabytes, and you just try to load the data and you run out of memory, and then you have to figure out something a little bit more clever just to handle that data. And one of the things we realized early on, and we'll see in some of the other pictures, is that large portions of it are actually blank. Like you have a whole bunch of regions that just don't have any information. And so we originally started with one of the starter kernels on Kaggle, and we just kind of adapted that and kept iterating. And one of the things that we had to modify right away was it was doing a whole bunch of training against these blank images, and it was just a waste of training. We could immediately make things converge faster and have less training steps by just skipping over all of the blank segments. So that's a little bit about the data. Looking at the model, I've mentioned this a little bit. We're doing 3D to 2D, and we have to figure out how do we bridge that gap. We don't know where the ink is in 3D space. We just have to kind of condense it down to a 2D map. And one of the things that we spent a whole bunch of time talking about was just how do we handle depth and variance, because we don't know where the ink is, and we want a model that we can apply to any depth and get a good value out of. So that was like kind of a must-have for us, is like, how do we make it so we don't have to choose the layers that we're picking from. So I saw in a lot of the different discussion posts, people are doing things where they're saying, okay, I'm only grabbing layers 24 through 32, or I'm going to do 3 different crops of 24 through 28, and then 25 through 29, and then all kinds of stuff like that. And it was very customized to the data. And we were trying to get something that was general, that would make it so we didn't have to tune to that stuff, because that seemed a bit dangerous to us, because there's no guarantee that the ink was going to happen in exactly the same layers in the test set. And so the first model that we started with was a 2.5D one, where you basically take the depth and then you just set that as channels. And that was kind of the thing that triggered us to look at depth and variance, because that approach actually learns which layers have ink and which ones don't. And so we realized if we go to the test set and it's just 3 layers up has ink instead of a different one, you would end up having terrible performance, because it wasn't putting the correct weighting to the correct layers. So that was very important to our approach, is understanding how do we make it so we just throw in as many layers as we can fit and let the model figure out what we're doing. Because having depth be something it learns was bad for us. We didn't want that to happen. So other properties that we wanted it to be rotationally invariant and flip invariant. And we didn't entirely understand why that was the case. I think some of the people in the discussion pointed out why that was better. So the person who ended up getting 6, they had this interesting technique where they figured out that it seemed like the fragment A and the fragment B were actually part of the same fragment, and they just got sliced, and they were rotated horizontally. And so we saw in the discussion that people were getting huge performance boosts just by doing TTA. They're just running prediction on the same fragments, but rotating it 90 degrees multiple times. And so they were seeing like that seems to disproportionately give us a boost in performance. And so we wanted a model that was just inherently rotation and flip invariant, so we didn't have to worry about that. And we ended up using TTA anyways, but ultimately we wanted that property because we saw what was happening on the leaderboard. And we said, well, we can just rotate the images ourselves and be strong to any orientation, and then we're good to go. We don't have to worry about it too much. So one of the things on the metric that Ted was calling out is we were optimizing for the F0.5 instead of the F1. And so what comes out of that is you're focusing on precision more than anything else. So you don't want any false positives. False positives are poison. So we wanted a model that could optimize for that, and we could easily pick a threshold that would give us an optimal value for that. And so whatever we could do to make it easier to pick a threshold and get a good outcome out, that was what we were optimizing for. And then bonus points if we can do it fast. So some of these models are pretty heavy and you don't want to spend 3 hours doing predictions if you can do it in 1 hour, because that means that in the Kaggle environment, you can do 9 models instead of only 2 or 3. So those are kind of the things that we were looking at and optimizing for. And so here I'll show a little bit of what our approach looked like in terms of the modeling. So I mentioned before that we really value the depth invariance. We want it to not learn that depth is important. We want it to basically be applying the same model to all of the different depths and aggregating that in some way that it doesn't learn that pattern. And so what ended up working really well for us is we basically took our input, pass it to a 3D model, and then that outputs another 3D volume. And then after that, we crush that 3D volume across the depth axis, and then we pass that to a 2D model. And so walking through what those shapes kind of look like. So imagine you have 8 in your batch, you have one channel because we only had one channel in this competition. And then we took the middle 16 depths. So we have 65 and we already crop it into the middle 16. And we say, these are the ones that we think have ink. And we have a little graphic at the end that we can show that will kind of point to why we made that distinction. There might have been more in other layers too, but we did well enough with 16. And then we took height and width of 1024. So we have this big 3D volume, and then we're passing it through some 3D model, and we'll talk about what models those ended up being. But what this model does is it will expand it out to multiple different channels. So we had one channel, we expanded out to 16 or 32 or 64 output channels, and the depth is still the same, the height is still the same, the width is still the same. And then what we do is we take the max pool of the depth. So we basically say just find the max across all of the different depths. And then it makes it so now we have 8 by 16 by 1024 by 1024. And this 16 is from the channels, it's not from the depth. The depth completely goes away. And so this is where we introduced that depth invariance, is we basically said, apply the same thing to every single depth, or only pass out the maximum intensity. And so these channels substitute out for the depth. And it's no longer looking at that in particular. And then now at this point, we have a 2D image. We have 16 channels, and we can pass this to any 2D model that we want. We can pass this to UNet, UperNet, SegFormer, mask former, whatever. Like there's endless 2D segmentation models that we could have passed this to. What we ended up finding the most success with was SegFormer. And that one was kind of funny because we discovered that because people were asking if the license was okay in the discussion. I don't know that we would have found that on our own, but I just kind of looked at the discussion and I saw everyone say, hey, can we use this? And everyone who was asking if they could use it had a high score. And so I was like, I'm going to copy off their notes. So I borrowed SegFormer off of all the people I saw doing well on the leaderboard. And so after the SegFormer, we get the output here. And one detail about this is SegFormer actually downscales things when it's going through all of its layers. So instead of it really being 8 by 1 by 1024 by 1024, it's outputting 8 by 1 by 256 by 256. So it's a quarter the size that it originally was. And so I did some simple upscaling after that. So it's actually outputting a smaller segmentation map. And I think that was one of the strengths of the SegFormer, was it's actually doing a coarser classification. And so it's not getting as confused by all of the little edges and details that it might be missing. And we saw that it made very kind of complete masks. It didn't have holes in it. It didn't have any other kind of discontinuities. So talking a little bit about what those 3D models and 2D models actually panned out to be. So we started with the 3D UNet, and we said, okay, 3D volume into 3D UNet, it outputs an identical volume again. And then we passed that into our SegFormer model. And then we tried, well, do we really need a UNet, or can we just do 3D convolutions? And we tried various different flavors of that because we realized we don't really want it doing classification at the 3D level. We just want it doing some 3D convolution so we can get that Z invariance. And so we did a bunch of experiments with just 3D CNNs, saying like, what if we do a filter size of 8 by 1 by 1, so that then it's like invariant eight dimensions in the Z axis, and it can kind of slide along, and it's not really learning anything in the XY on that side. And we did a lot of different permutations of that, saying like, well, what if we only learn XY? What if we only learn depth? What if we do more layers? What if we do less layers? How do we capture that? And so those models ended up being pretty good because they were much faster to train. So the 3D CNN was faster to train than the UNet. But in the end, it wasn't conclusive in local validation if one was better than the other, but on the leaderboard, it seemed like the UNet was better than the 3D CNN. I just kind of looked at the scatter plot of like, here's our scores, and the UNets just seem to tend to be a little bit higher. So let's kind of focus on that one. And then to that end, we were going like, well, let's just try bigger. Let's go even more 3D strength. And then we went to the UNetter model, which is a kind of transformer addition on top of the UNet. And so that's what this architecture is over to the right side, is the UNetter model. And so that was a difficult one to integrate. We looked at various different libraries, and we found one in the medical domain. And so we got that working. And so I'll show on the next slide what the code looks like. It's actually very, very simple. We didn't have to do a whole bunch of kind of custom stuff. It's just a stack of a few different function calls and layers. So that's it for the 3D stage. There's a whole world of 3D models out there that we didn't explore. We saw some in the discussion, like the NN UNet, NN Former, various other things like that. So those are the ones that we tried, but my intuition is that whatever is the best 3D model would have done well there. And so the UNetter was the best that we tried, but there's probably even better out there. It seemed to be the trend that whatever the best 3D segmentation model plugged in there was probably going to continue to improve results. And then moving to the stage 2 2D models, we tried 2D UNets with various different backbones, and those worked significantly worse than the segformers. And I don't know if that's because of the architecture itself or because it was making predictions at a higher functional resolution. It was outputting at 1024 by 1024 instead of 256 by 256. That was unclear. We never tested that. So it might have been the case that we could have done 2D UNet there and gotten good results as well if we just kind of left it at an earlier branch of the U and output at a lower resolution. And we also looked at the UPerNet, and we tried to get mask to former going and various other things, but we didn't really get them integrated and trained. And I'm not sure what was going on, but the transformers package, we couldn't get it to do the right dimensions for us. There's a question about pre-trained weights. So for the UNetter and UNet and 3D CNN, those are trained from scratch. There's no pre-trained weights for those used. For the segformer, we used the ones directly from NVIDIA, the ImageNet pre-trained ones, so that MIT, B5, B3, whatever, all of the stuff that's on Hugging Face. So that's what we used on those. So the second stage was pre-trained. The first stage was never pre-trained. And so as I mentioned, kind of like better on paper seemed to be better in the problem as well. We had noisy signal in our validation, so it didn't always become clear, but on leaderboard, we seemed to see that trend hold true. So the fanciest 3D model that did the best on the academic papers did the best on this problem as well. And same thing with the 2D stage as well. So we found that on the leaderboard, the B5 did better than the B4 and 3 and 2 and 1. So that was the kind of pattern that we saw. And so we didn't pick that up until all the way at the end. And then at the end, we were kind of like just I called the model jumbo, and it was like, let's just do maximum everything and try and fit as much in as we can. And so some of our models at the end did extremely well, even just single models, but it was like, here's the biggest that we can possibly fit. And so we'll see on the next slide. So this is what ended up being our best single model, and you can see it's not super fancy because it's calling other functions to get the majority of the layers in the work. And so you can see what we did is we have the unetter that we call from the unetter. I don't know how to say it, MonAI, MonAI. That's where that came from. Basically, we just pulled their implementation. And we say, okay, we have one input channel, we have 32 output channels, we have 16 depth layers, and then we have 1024 by 1024 or 512 by 512. It just depends on the model that we're training. And then we have the segformer, that NVIDIA pre-trained one I was just mentioning. It has one single output channel. We give it the 32 input channels that came out of this 3D model. And then because of the downscaling here, we had to upscale it a couple times. So doubling from 256 to 512 to 1024. And then if you look at our forward pass, we pass it through the 3D model, and then we just take the max across the depth axis, like we mentioned. And then I did a little bit of dropout, so just 0.2 or 0.1 or something. And that was dropping some of the channels. So we have 32 output channels. It's only getting 80% of them every time on the forward passes, just to make it a bit more regularized in between those different stages. And then you can see that like we had a single model that was scoring 0.824-ish. So that would have been first on the public leaderboard at the time. And then it was getting 0.673 on the private. So our single model ended up being very strong, but I feel like we left some performance on the table in terms of the ensembling and stuff. So we didn't carry it much further than that, even with our stack of 9 models. So talking a little bit about our training procedure, I mentioned already that we skipped the blank images. So we have all of these regions where there's just no input. So there's nothing to even learn there. So skipping that made our training go much faster. It prevented our model from biasing towards 0. It helped us in several ways there. Like a lot of people, what we ended up doing was we were training against the binary cross entropy and the dice loss. And so the dice is good because it's directly what we're optimizing for in the competition, roughly. It's not the 0.5, it's just the F1. But its big problem is that it's just not as continuous and smooth as the binary cross entropy. So the binary cross entropy gives us a nice kind of optimization signal, and the dice gives us that, like, here's what we're actually trying to optimize for in terms of the leaderboard. And so the combination of that seemed to work well. We didn't test that as thoroughly as we probably should have. We basically went, here's binary cross entropy, here's binary cross entropy plus dice, and we just never turned it back off. So I don't think we ever even tried dice by itself. So maybe that's better. I don't know. One of the things that we used that helped us a lot was stochastic weight averaging. So basically through the epochs, you're averaging with the previous epoch's weights, and you just slowly do a moving average of your weights. And that makes it so that your optimum epoch stays for a lot longer. So if you look at our training curves, like down here, they're varying a whole lot. So you can have one epoch that does, I don't know, 0.52, and then you have another one that does 0.58. And so having that super noisy signal makes it hard to tell exactly if something's better or worse. And then you don't know which checkpoint to use on the leaderboard, and all kinds of problems like that. So the SWA seems to help a lot in terms of final value. You get better better overall predictions when you take the moving average like that. But the other thing is it makes it so you don't have to worry too much about the checkpoint selection, because you just kind of have the moving average of a whole bunch of checkpoints, and it gives you this very smooth optima. So if you pick 30 epochs versus 50 versus 70, it's not really too different. You'll end up getting a pretty decent result regardless. In terms of our validation procedure, we kept validating against fragment 1. That was just our constant validation. We didn't do k-fold. We didn't split fragment 2 in 2 pieces. We didn't do anything else like that. We just basically said validate against fragment 1, see how it does, see if it's directionally better. And then if it is, then we go do a retrain, and we say train against all of the available data. So fold 1, fold 2, fold 3 with the same with the same parameters and number of epochs and everything. And then we would go and we would use that on the leaderboard, and we would see, okay, did our improvement improve on our local validation and our leaderboard? And if that was true, then we would keep that model around, because we had that kind of second phase of validation there. We did cosine annealing learning rate, so you can see it kind of tail off. I don't think that the learning rate was particularly important to us. I tried with gradual warm up on and off, didn't really make a difference. With it on, it seemed to slow our training down a little bit, but we just kept it on just because we didn't have conclusive evidence that it was hurting anything. So we said we can just eat the extra 2 epochs and just train a little bit longer if we have to. That doesn't make a big deal. And one of the early things that we realized was that larger crops helped performance quite a bit. So you can see this graph on the bottom. So this blue line is what 128 by 128 does. The orange line is 512 by 512. The gray line is 1024 by 1024. And so basically we realized just expanding the XY context gave us better performance. And so in a lot of competitions, if you do higher resolution, that means you're training slower and you have all of these other kind of compute budget problems. But in this, because we were taking crops of a single image, what ended up happening is if you do 128, you're doing, 64 times more crops of the 128 by 128. But if you do the 1024, then you're doing way less crops. And so you're actually doing the same exact amount of compute. So 1024 was not more compute intensive than 128. It was just less steps of bigger images. So that was kind of a nice property that we figured out, is we can just keep doing bigger, and then it gets better performance, and we don't have to waste any more compute on things. And so you can see that like this is a pretty significant gain in performance for 0 additional compute. It's just setting a parameter differently. So in the end, our final submission was this big ensemble of 9 different models. And I think that this was kind of crucial for us having stable performance, because if you look at our models individually, a lot of them might have varied optimal thresholds. So for some of them, like in this one, this is one of our best models. And on local validation, it was saying that its best threshold is all the way down at 0.1. And if you look at where it would be at 0.5, it's losing a significant amount of performance in terms of the leaderboard. So if we did a submission with this and it turns out 0.5 kind of a crappy threshold, then it would have showed up as a terrible model and we wouldn't have known. We would have just said, well, it was a shitty model. So what do we do with that? But what we found is even if a model was bad on the leaderboard individually, if we knew it was good locally, we could kind of throw it in the pile and all of them would just average out in the end, so that it would be calibrated to 0.5 eventually. So with all of these models stacked together, we got good performance. And we even, like our last submission at the dying 30 minutes of the competition was just what happens if we scooted up an extra 0.55 and it didn't do any better on the public leaderboard. So we just said, okay, 0.5 is perfectly fine. We'll just stick with that. So that was our big ensemble, and you can see kind of the composition that we used, various different UNets, various different segformer backbones, some 3D CNNs, and then the UNetter model mixed in there. So these ones ended up doing the best. So we had the UNetter into the massive segformer B5, and then you can see that we got 0.82 with that one. And we also Ina did some multi-class work, seeing what if we change it from doing binary prediction to it's predicting all things at once. So it's predicting the ink, the mask, and the background as separate things. And that actually kind of led to some interesting results. But that was right at the end of the competition, so we didn't get to explore it too much. But just visually looking at those masks, it looked better because all of the areas where it had papyrus, it was just zeroed out. It wasn't noisy like the other ones were. So that was kind of an interesting property. Instead of it being binary and being kind of confused on what was mask and what was ink, it was much more certain in that regard. So maybe worth further investigation. One of the tricks that we threw in that might have been the extra inch that took us across the finish line was this post-processing function. And this is something that I knew about from an old cloud competition. So we were segmenting out clouds, and then there might be tiny little stray pixels throughout the segmentation. And you knew that if it wasn't many pixels in a group, then it probably wasn't an actual valid prediction. It was probably just some sort of noise that fooled the model. And so what we do is we apply the CV2 connected components to it, and we say find all the blobs throughout the image, and then anything that had less than a certain connected pixel count, just discard it basically. And so what we ended up doing is anything that was under 10,000 pixels, we just threw it away. So you can see stuff like this. So this little segment here disappears in the post-processing, and this over here. And so we did some tuning locally, saying pick different thresholds, pick different minimum sizes that we allow through. And if you really tune that, you could get a very significant gain. But we kept it pretty conservative because we didn't want to risk like a whole bunch of stuff just being deleted out of the model that was valid. So locally we saw that there was some benefit there, but not consistently enough, and we didn't really apply it to the leaderboard because it seemed a bit risky. So that's kind of the gist of our solution, but one couple other things that I want to show is one of the first things that we did was just train a model against two of the fragments and then validate it against the third, and just sweep through the different layers basically. So we train a model against fragment 1 and 2, layer 1, and then we apply that to fragment 3, and then we just sweep through all of the different layers, and that's what this curve is. So you can see that up until layers 22 or so, there's just no signal. You can't find anything in there. And so that's what kind of informed our strategy of just only take the middle 16. And so you can see that each of these lines, each of these kind of separate scatter plots, they're a bit messy. I couldn't get it to show the colors for each of them individually. But you can see that the different ones have different amounts of predictive power in each of the different layers. And so this kind of informed some of our strategy, just understanding that there's no information there, so we might as well just throw it away. So that's one of the fun plots. And then the other one was, so we have the output from the 3D model, and then we're taking that and we're crushing it on the depth axis. But something fun that we can do is, instead of crushing it, we can just inspect it before it gets crushed on the max across the depth. And so you can see this is sweeping through 24 different layers of the depth. And you can see that like on the earlier layers, it's seeing stuff over on this left side. And then in the deeper layers, it's seeing stuff more on the right side. So in some way, you might be able to kind of back out of the 2D labels into 3D labels, basically by inspecting the model's output and what it's learning from. And so this is just something that I put together yesterday. We ran this experiment like day one, but we never really used it. And I just finally put it into the video form yesterday, and it's interesting to look at. Before we just had a dump of images and it was kind of hard to see the pattern. So I thought that was interesting. So that's all that we have to share. Anyone have any questions, or Ted, anything?
Alex, I think there'll probably be a lot of questions. Let me just say, Alex, Ina, first, any rapid fire other things you want to just add, and then we'll just like open things up.
Not really. I think one thing that I think we did really well was I think we were pretty organized about experiments. So we had a shared WANDB going, and we, Ted's showing it. Ted's showing it here. So, or sorry, Ryan's showing it here. So we, and anytime there was a new result, we would post on the Slack and discuss what was happening. And I think that was really helpful for sort of the teamwork aspect of pushing us in the right direction, right? We would share knowledge very, very quickly and then iterate fast. So, so I think that was pretty nice. Do you have anything to add, Ina?
No. Plus my audio is kind of messy. So
yeah, I switched to the MacBook Air microphone, so hopefully that's a little bit better, but
that's all right.
Yeah.
Yeah. Thank you for the presentation. I think it was great, and it summarized really nicely all the work that we did.
Yeah. So Ina and I, we actually just saw the video of the like none of us had seen that video before. Ryan posted it like 20 minutes before this presentation started. So we were like, oh, that's so cool. I wish we saw that before. So yeah.
And it's interesting, right? Because I feel like it was our first competition, so I was kind of like expecting that towards the end we wouldn't have anything else that we would want to try, right? And then we would be like done with it. And actually, like, if you had given us like another 2 weeks, I think we still had ideas to like run with it for another 2 weeks, right? So it was definitely exciting, and I think Brian is totally right? We had a moment where we were like, oh, we'll never get this thing to work, right? Like our local validation was showing numbers around like 0.5 or something like this, and people had like 77 in the leaderboard, and we're like, how the heck are we ever going to do this? And then all of a sudden it worked. Ryan got a model that worked super well, and we were all like super excited, and yeah, it was really fun.
Yeah, I think we jumped from like some super low place down to like rank 8 in like one run, and we were like, whoa. So that was really fun.
Ryan's magic.
Yeah.
I answered a few technical questions in the chat. So I think the only thing I'll add here is sort of a non-technical comment, that we actually entered the competition kind of late, and I entered even later than the rest of the team. So it was like less than 3 weeks to go. So for me, there was a definite bias on finding models that like were, depth invariant and whatever, like doing things that should generally work well, even if there's domain shift from the training set to the test set. So if the new fragment is warped, so that from one end to the other, where the signal is changes, if it just is deeper Z-wise than the other one, it turns out something that people were talking about was the test set was actually rotated. So the text was like vertical sideways instead of horizontal. So for me, it was just like, yes, we're going to bias this towards solutions that are highly general. And, we joked about some stuff like, oh, well, theoretically, if we had more time, we could do like the initial predictions, and then we could layer on some model that like looks for rows of text and, like do some kind of like LDA analysis of rows. But it was like, no, we're not going to mess with that. We don't have time. We just got to go for something that's like very general. So I loved some of the other solutions that people did, and kind of jealous that we didn't think of some of those things, but that was part of the bias. If you look at our solution, in some ways it was very simple because we just couldn't afford to take time on some of the riskier possibilities. All right, so with that, I think I'll open the floor to other competitors if you want to add anything about the competition in general, anything that you tried, and then we'll just go to like general Q&A.
And maybe give me 2 seconds. Maya has asked me to reintroduce myself, so I'll do that now. I'm Aina. I'm originally from Spain. I studied with Alexander. That's how we met. And I moved to San Diego about 1.5 years ago. And I don't know, just recently with Alexander moving and everything, we decided to like find a community, right? I found it really, really hard after grad school to find people that were, I'm a nerd. Alexander and I read textbooks for fun on the weekend, right? So I found it like really, really hard to find a community that wanted to do the same and that was like excited and wanted to learn and wanted to do things. And I'm really, really happy that we found that in Ted and Ryan. That's me. And one last comment, if people want to join like SD meetups, I would like love you guys to do that. Like it is really fun. I'm going to assume that most people here are nerds, so I highly encourage everyone to come. It's great.
Thanks, Aina. Okay, so I'm going to give sort of first preference to people who participated. Anybody want to share or ask a question? Yeah, I see a hand raised. Patrick, go ahead. And then anybody else, if you want to just raise your hand, Zoom will automatically queue everybody.
Howdy. Awesome presentation, Ted and folks. Thanks for doing this. So typically when I approach any sort of vision-based machine learning project, I like to run some just standard CV, like traditional CV analysis on top of the project. I actually took a stab at it with this project when it was first released, just for about a week, just kind of poking at it, and I really couldn't tease anything to the surface. I found it pretty difficult. Usually, most problems you can sort of tease something out, right? And I'm curious if you found that to be the same, or if you sort of just jumped straight into the ML side of things. And then what, more generally, I guess, what was your very super early analysis like?
Yeah, I'll let the other team members chime in because they actually kind of got a head start on me. What I'll say is I put this in the chat that like it is not just simply the intensity of the pixels, voxels. Like that would have been just very, very easy for us to find the ink. So I think it is a more complicated pattern, especially because the ink, when you write, it penetrates a certain depth into the papyrus, but it doesn't go all the way through. And I think that that's a good part of the signal that we were detecting is where in the higher surface layers, the pattern was different than the deeper layers where it was pure papyrus. And then because these are not like perfect things, we're just X-raying and re-2D'ing something, there's also air signal, and there's varying height of the thickness of the papyrus. So I think, yes, I agree. It's pretty complex. Anything you guys want to add?
Yeah, I mean, I played around in Photoshop a little bit, like with some of the areas that we knew that there was ink in, trying to mess around and get like the contrast such that the ink was popping out more, and then use those. But it just like didn't do any better, and in fact did worse most of the time. So it's definitely, the ink certainly wasn't in the intensity, and I think yeah, I don't think any other sort of visual pre-processing stuff that we did worked out.
So I think maybe one thing worth noting is that we actually started with an EDA, I think they are called, that was already in the Kaggle competition when we joined, that did a really interesting analysis. That one was based on intensity, but that kind of like swept through all the layers and kind of like nicely showed, right, that you started with less information and then that all of a sudden you started seeing different intensities, and kind of like we based it off of that, and we did some texture analysis to kind of like get some intuition. But yeah, just like looking at the layers, it was really, really hard to see anything with the naked eye. Maybe if you squinted and had a little bit of imagination.
All right, go ahead, Kevin.
Yeah, so I had a question. So basically, starting from the beginning, you have IR, X-ray, is that 256, and then going through, and especially at the end, did you have the option for multi-class classification? If so, was it too computational intense, or could you gain anything as far as accuracy in anything but binary?
I'm not sure if I understand the question correctly, so I'll answer what I think you're asking. So we originally started thinking of doing binary, and that worked, and that gave us results. So it wasn't really until the end when we were trying to get the model to work better, where we started like exploring ideas such as doing multi-class. And I think my main thought behind doing multi-class classification is that it would help us differentiate between kind of like that softer background of the papyrus and the letters, if you actually told the network that it was supposed to expect something there, right? And what we visually saw is that it seemed to help reduce some of the false positives that we're getting, but it's hard to tell you, and I didn't really have numbers because we didn't get to run those experiments, right? It was a little bit computationally expensive, but not necessarily more than any of the other networks. It's just, it did take us like, I think one full run of the model was like about like 10 hours of training or even more, right? So we just had so much time to try things out, and it was towards the end. So we said, okay, let's do one, put it in the ensemble, and that's it. But definitely something that I would like to explore more if we had the time.
Okay, so you're saying mostly runtime it would have taken?
Yeah, but just like any other run, right? It just, we started with that idea late. Like it wasn't more expensive than training the regular network, if that's what you're asking.
Okay.
Like it was just as expensive as training the binary.
Thanks for the question. Hey, Steve.
Hi there. Yeah, congratulations on your winning the competition, and thanks very much for this presentation. Yeah, my model, I was using like a 3D ResNet, and the main problem I was having was the amount of time it took to train. And as like Ryan said already, Kaggle's resources didn't really sort of offer enough computing power to train anything really. Yeah, so like I ended up like I was training on Google Colab, but I just really wondered what platform you use for training. And as I say, my models, each model would take maybe sort of 12 hours to do it. So how did you train your models? What platform was it on, and roughly how long did things take?
We used GPUs from Vast. Well, Aina and I did, and then Ted did at the end as well when he came in. I was using an RTX 4090 from Vast, and we had like a whole
sorry, what's Vast?
Oh. Yeah. So that's actually
I can show it.
Yeah,
you guys
please.
can talk, but I'll show the site.
Fantastic.
Yeah.
Thank you, Ryan. I think the biggest thing for us, so we came from like doing work like with our respective companies, right? They have AWS and whatnot. But so this was a huge experience for us in like trying to get all of this system set up. VAST, what Ryan is showing right now, is a system that allows you to rent GPUs like per hour. And it was a whole thing to get it set up because you still have to like download the data and get everything ready, right? So maybe it's a little bit less easy to use than Google Colab. But for us, it was definitely worth it because just like you were saying, right? Like in Kaggle, we couldn't even load the three like slices, right? Yeah. And so yeah, that's what we use. We tried renting out different types of things you could explore, like with even like getting multiple GPUs and parallelizing, but of course like that costs more money. So yeah, that's how we train.
Yeah. And then once we trained it, we had an inference notebook that was on Kaggle, and then we would run the models that we trained set like in different places on the inference notebook on Kaggle.
All right, thanks very much. Yeah, like one thing I'd found was, originally I was using like the 3D ResNet inference notebook that the person had put up, but they weren't using like AMP in their inference. and so like it was really slow. And as soon as I put that in, it sort of became 5 times faster. So like it let me build an ensemble there where previously I couldn't.
And
Yeah,
Steve,
we definitely had mixed precision turned on, and then by the end, you know, Ina spun up a second one. So by the end, we had like a triple A 6000, a double A 6000, an A 5000, a 4090, and a 3090 that we were
I wanted
all
to get the
trying to train on.
multi-class really trained. I was really trying to get that multi-class trained. Steve, but if you're really interested, maybe like offline, feel free to like Slack Alexander or I. We really have set up probably at this point like 15 instances each. So I would be very, very happy to like show you how to get everything set up, the small nuances of like, right, what kind of Docker image to set up and all of that. So
That'd be brilliant. Thanks very much. Cheers.
Yeah.
So just background on what VAST is, though. VAST is like a marketplace where research labs or whoever else can go and say, like, we have excess compute that's sitting idle, and they can just sell it to you. And it's much, much cheaper than AWS or whoever else. And so you can get much better prices. And I used this for a while. And now at work, I have a triple A6000 system that I get to play with. So I haven't needed to use any VAST recently, but I recommend it for anyone who doesn't have that luxury, because it gives you much better prices. The downside is that the reliability and availability and everything is not as good as AWS. If they decide that they're taking their system off the market, you just lose your work and it doesn't come back online. So you have to be a little bit careful. You have to back up your stuff. You need to know that if you're turning your system off, someone else might rent it and take it away from you. So just word of warning.
I think that's the biggest advice. If you guys are going to use VAST, my biggest recommendation, we didn't really have a lot of systems actually turn off, but what happened every single time is if you turn your instance off, they will take it. Someone else will take it. I'm thinking there's a lot of people just that need GPU. So every single time we stopped an instance, it disappeared. So if you guys want to use VAST, I highly recommend that you just account for the fact that that instance will be running all the time, or that you will have to set up a new one.
That's great. Thanks very much.
All right, thanks. Appreciate the question. Yeah, we can take the next person.
Hey, hi. So, like, I was really surprised on how our ideas matched. The only differentiation that I found from our ideas were I wasn't predicting the Unitar's output to have 32 channels. Instead, I gave it as one channel, which ended up having worse results than what I got. But I was actually trying out combinations of Unitar plus MIT B5, but that didn't give us good results. So I had to chuck that idea out, but it seems pretty interesting that with more channel as output, you guys were getting better results. Only thing that I wanted to know was, like, how did you guys manage the VRAM issue with 1024 inferences, like for training as well? Like, what batch size did you use and other things?
We had to scale our batch size along with the increase in size. So we were running things at fairly small batch sizes at the end. Like, we were even on the big GPUs that I have, I was down at 4, 6, 3, stuff like that. So we were splitting across multiple GPUs, and even then we were ending up relatively low batch size. But I mean, like it was mentioned before, mixed precision, really important. Anything you can do to reduce the VRAM, very important. But yeah, I mean, part of it is just having the hardware that can fit it in.
Okay. One final thing that I wanted to ask. So what are you guys going to do with the money?
I don't have anything planned. I don't know if you guys have interesting plans.
Haven't talked about it at all.
I don't have any specific plans, but I did tell all my family members that they are each going to get an opportunity to get themselves something because they've been putting up with me disappearing for the last 2.5 weeks.
I was genuinely just thinking that that's what we will need to like cover costs, and then for other competitions that we want to join, right? Like renting GPU is not that cheap.
Thanks for the question. All right, Luke, you got your hand raised?
Yeah. First of all, thank you guys for doing this presentation. This is really incredible work. I'm curious, when are you going to release the code? I wanna try this myself and everything.
There's nothing stopping us. I'd probably want to do a little bit of cleanup. I don't think it might take a lot of instruction as is. We have stuff in a repo that we could throw up on Kaggle. I figure people are probably just most interested in our best single model. But yeah, you're going to need a little bit of hardware to run it still if you want to train your own model, if you want to do inference and everything. But I mean, there's nothing stopping us. It's just a matter of time. We finished the competition Wednesday. I was in San Francisco, and when that happened, and then I flew back 2 a.m, and then I wrote up our solution, and then now I'm here. So once we get time, yeah, we'll do that.
Awesome, thank you.
I was going to say that we can clean up the repo, but that will take some time because right now that isn't.
Yeah, we had a GitHub repo where we shared code, but there's like hundreds of experiments on it right now that are like super messy, and all of the code is copy pasted and stuff. So like, you can see it, but it is currently like not pretty.
Yeah. So
yeah, I think we'll go for like one cleaned up of our like good model that we then post. All right, awesome. Loving the questions. Anything else for the other people who participated? JP wants to know, are you guys gonna continue with Scroll Prize and try and see if you can run your models on the larger data set?
I would like to. I think it's worth a try. I don't know if we've got enough here. I think that it's probably better than what's been done. I don't know by what margin. You can definitely look at this stuff and you can read a little bit of it. So I think it's worth a try, but we've got to adapt it, run it on some new data, and see if it's possible.
Yeah, I think I needed just a little bit of a breather after the stretch run at the end of the competition. I was like, up till 3 a.m. every day, and then stupid work was scheduling 8 a.m. meetings. Like, what the hell? But in particular, like, I have this idea that some of the stuff that Ina knows from medical imaging, that if we can pre-process the data, we don't have to necessarily even know exactly what the right pre-processing is, but if we can augment a number of channels with pre-processed data, that then the architectures that people are using, these are sophisticated enough that they will pick out if one of them has additional. So like Alex was saying, what if we tried to just like transform the data into the frequency domain? Yeah, I think that's worth a shot. If it doesn't work, then the model will just ignore that channel and, put 0 weights on it. So I feel like that's something that we need. I just don't feel like we necessarily have enough right now to be able to say like, oh yeah, here's this little, 2-centimeter patch and we can read, 15 letters off of that. I don't think we're quite there yet. All right, this has been a lot of fun. Yeah, and actually, I'm not concerned at all about losing resolution. So going to 8 micron instead of 4, I think that's fine. You heard Ryan say that the actual, downscaling might have actually helped. So So at least personally, I don't know how other people feel, but I'm not at all worried about going to 8.
Ed, we found someone who's reading the Kevin Murphy book.
Oh, look at that.
Your buddy.
You can join our other series of meetups.
You should.
All right.
No, you could. You should.
All right, thanks. You guys have been a great audience. We've had a lot of fun sharing with you. And if you guys are interested, it's only been a couple days. There are going to be many more posts, I'm sure, from people who participate in the competition on the different things that they've done. And then again, scrollprize.org, super cool website, has great information, great tutorials, and win yourself a bucket of cash. All right, thanks everybody.
Thank you,
everyone.
Thanks, guys.
Bye-bye.
Thank you so much.
Thanks, Mike.
Cheers, thanks. Bye.